Some work we've been doing recently at Stanford on detecting earthquakes, in particular detecting very small earthquakes. So this is, I'm a seismologist, so I'm in the geophysics side of the spectrum at this meeting. But this project involves people in the, Terry Ann Logan, who's a grad student in computational math and engineering, and lately several computer scientists who have really made the technique realize its full potential, closer to its potential. So what I'm going to be talking about is earthquake monitoring across scales, and whether, or an approach to earthquake monitoring which applies across scales. So whether we are interested in monitoring at the planetary scale or at the laboratory scale, the task before us is essentially the same. We want to detect earthquakes or events. We want to locate them, we want to characterize them. We understand, we want to understand as much as we can about what they're telling us about the deforming interior. So what I'm going to show a couple of examples, one at the reservoir scale, one at the regional scale, but these sort of approaches can apply at really at any scale. So this is a picture of Charles Richter of the Richter scale. A seismologist who's an undergrad at Stanford, a physics major, reading a seismogram. And so when we read seismograms using analog data, we typically pick the first arrival time of the P wave, the fastest moving wave, and if we're lucky, the S wave as well, and we try to locate the earthquake based on that. And so this is a classic helicorder recording system. Basically, there's a 2-day-long helix that gets wrapped around these drums, and we read seismograms from that. It wasn't that long ago that this is how data was recorded. So we went digital in earthquake seismology in the 1980s to 1990s. So there's a lot of this sort of legacy analog, what computer scientists would call dark data. Anyway, the situation has changed completely. So we're now all digital. The data volumes are growing rapidly. We're accumulating data linearly with time as data is now saved. We didn't used to save all of our digital data. Michelle showed very clearly how useful that continuous data is in his talk yesterday. Also, we have what are called large N networks, so seismic networks with hundreds to thousands to in the neighborhood of 10,000 nodes. And so this shows the Long Beach. Two faces of the Long Beach array. Each one of these dots represents a seismic station, and there are thousands of them. So we have, and these are recording continuously 24/7 for weeks to months in this case. So we absolutely need algorithms that can help us extract all the information we can get out of these massive, what for us are massive data programs. So I'm going to give you a little bit of a background on where seismology has been recently, and then try to suggest where I think it's going to be going. So this
what was the length scale of that you just showed on the map?
This dimension, this is 7 kilometers, and this is 4 kilometers. So this is Long Beach Harbor here. You're from Caltech, right? Yes, probably a 3-hour drive. So the standard approach to detection or location is we look at individual streams of data, and we look for some impulsive arrival. So what we do is we square the signal, we take a short-term average divided by a long-term average. When it gets above a certain threshold, which depends on the noise and the recording environment and whatnot, then that station says, hey, something's going on. If enough different instruments say that, and if the sequencing is consistent with waves coming out of the Earth, then we declare an event. That process is called association. So we associate these individual phases with an earthquake, then we locate it and characterize it and go on from there. So this approach works really well when events are big enough to be recorded at 3 stations, that is enough to locate the event. I've already said we're interested in detecting small earthquakes, so this is going to be somewhat problematic. The events have to be somewhat impulsive, so that threshold is reached, and the events can't overlap because then they would interfere with each other's detection. So standard approach works well, but there are important cases where it doesn't. So when we have weak events, such as these are individual seismograms, time increases from left to right. These are a newly discovered kind of earthquake called a low-frequency earthquake. They were not known about until about 15 years ago, and now they outnumber ordinary earthquakes and earthquake catalogs. And these were not detected by sort of standard processing because they're weak events and they have emergent arrivals. This is the same picture I showed you before, but now I've circled some small events that would likely be missed in standard processing. Earthquakes follow a power law. For each magnitude unit decreases a factor of 10, increase in the number of earthquakes. And so there's a lot of information that we're losing, at least on the temporal evolution of earthquake sequences, if we don't get all these little earthquakes. And finally, during earthquake swarms or aftershock sequences, such as this one in New Zealand, when information is just pouring out of the earth at a high rate, so these are superposed earthquakes, the STA-LTA method fails. Okay, so I'm going to show this diagram a couple of times. It's got 3 axes that measure attributes of earthquake detection algorithms. One is computational efficiency, that's the vertical axis. This is generality, and this is sensitivity. So STA-LTA, the algorithm I just outlined, scores high on computational efficiency, it's very fast, is somewhat general, so maybe it should be all the way out on that axis, but it's not sensitive. This is small earthquakes. So we can use a characteristic of the Earth that the structure is not changing. So Michelle in his talk yesterday showed some really beautiful results for Japan with bright colors and whatnot. That was a small fraction of a percent change in seismic velocity. So in first order, we can assume that the velocity structure of the Earth is unchanging, and if we have a repeating source, we'll get the same part of the Earth slips, they're called slips, we'll get the same source. And we see this in what are called repeating earthquakes. So what's shown here are 38 different earthquakes recorded on the Calaveras Fault near San Jose, California, happening over a period of 2 decades. Here they are just laying on top of each other. You can see wiggle for wiggle, these earthquakes, these 38 different earthquakes have the same signature. So if we know what that signature is, then we can look through continuous data to find repeats. So that's fine. So that would be a way to detect earthquakes. It would be extremely sensitive, much more sensitive than looking for the initial arrival, because we've got the larger S wave, we've got all redundant information that is telling us that an earthquake is happening. But most earthquakes don't repeat. So these events are a little bit unusual, and we need to detect earthquakes in general. So we can then sort of relax this assumption of strict similarity and look at adjacent earthquakes. So this is the same fault, Calaveras Fault shown in map view. This is a cross section, and each one of these circles represents an earthquake. There are something like 7,000 in this figure that happened over a period of decades. What's shown on the right in color are 3,500, a little over 3,500 seismograms. So instead of showing you the wiggles, I'm showing the up and down as red and blue. And what you see is lots of streaks. So this is something like 6 seconds of record. What this is telling us is the reason these streaks are there is because nearby earthquakes, adjacent earthquakes, have similar waveforms. So we can use this property, this less strict similarity, to find more earthquakes. And that process in seismology is called template matching. So it's basically a match filter where we take in red, so this is for a low frequency earthquake in Japan that's known about, the known signal from a different time period is shown in red. We use the individual wiggles, the signature of that earthquake, and we slide it continuously through time over, I think it's 18 channels here. And it provides and we take a running inner product, some inner product over all those traces. And that's our detection statistic, and it's very sensitive earthquake detection mechanism. It finds very small earthquakes, even if the noise is large. So this is just an experiment wherein we took the data during one of these low-frequency earthquake sequences, put an additional low-frequency earthquake at us in every, something like every 100 seconds at an amplitude of 1/10 of this amplitude, and then ran the detector on it, and 34 out of 36 times we found it. So these are really powerful detection methods that don't miss many events. That is, they have few type 2 errors for a reasonable type 1 error. And template matching, as called, has been applied with great success. So this is the Guy-Greenbrier sequence in Arkansas, an induced earthquake sequence. Here's a template or a seismogram of a known earthquake. We can run that through continuous data for a year or so, and we can find 5,500 similar earthquakes that can match with this known earthquake. So this template matching is a form of similarity search where we know what we're looking for. So we can call it informed search. It scores high. It's more computing than STA, LTA, but it's manageable. And it's very, very sensitive, so it scores high on both those counts. But the problem with it is we have to know what we're looking for ahead of time. We have to know that set of wiggles that is diagnostic of an earthquake unknown location. So it scores well in some dimensions. So you could imagine a sort of naive approach where you correlate everything with everything else. So all times with all other times. So you're still using similarity, but you're not making a priori assumption of what the shape of that similar waveform is. So here's just a number of windows of data, correlate everything with everything. That actually works, call it autocorrelation or self-correlation. It can be used to detect these low-frequency earthquakes within tremor. The problem with it, as you could probably anticipate, is it has very poor scaling properties. It scales quadratically with time, the number of windows that have to be compared if you're comparing exhaustively all windows with all other windows. So it's sensitive, it's general, but it's computationally infeasible. So what I'm going to present today is something, so it's not an ideal algorithm, but it's better in that it's computationally efficient, it's general, and it has high detection sensitivity. And it borrows technology from similarity search in other applications. What gave me the idea to do this was Shazam. I don't know if you've used that song identification app. At the break, we could do SoundHound. That's something where you actually sing a song, and it amazingly identifies it. We should have done that at the reception.
Could you demonstrate that for us?
Sing a song for us.
Well, so you know what I was going to do was to use there's a Google app that the Arts and Culture app will match your face, your selfie, to a museum painting. But Texas has biometric privacy laws, and Google is disabled in Texas, so I couldn't put that together for you. But if you travel, you can use it and match yourself to a museum painting. Same idea as this sort of similarity search. Okay, so we call our method fingerprint and similarity threshold fast. The idea is it's faster than the naive autocorrelation, and so there are a series of steps we have to take in order to get our detection results. Sort of the key steps, which I'll spend a little bit of time on, are feature extraction, that is forming a fingerprint, and then doing sort of databasing the results and doing fast, approximate search of that database for similar items. So first the fingerprinting. So this is Clara Yoon. This project is sort of the core of her thesis. That's a fingerprint. It's not really hers. It's nominally hers. But the idea is that we're going to take waveforms, windowed waveforms, continuously through time, and we're going to take those wiggles and come up with a compact representation of them that maps this, this binary representation back to the waveform. The idea is it's sparse. It also has to be diagnostic of signal versus noise, and I'll say a little bit more about how we construct that. And the idea is that we store these fingerprints in a database in such a way that we can query it very efficiently. So we take our initial time series that we're interested in detecting during. We form spectrograms, so frequency versus time that we don't. We discard the phase. We then window that spectrogram into overlapping spectral images. Typically, we do what's called a stride of 1 second. And then so then we take a transform of the transform. Okay, so this is our amplitude spectrum, frequency versus time, and these are coefficients of wavelet transform, the Haar basis that represents the shape of that frequency spectrum. So we haven't done much compression yet, so that's the next step that we have to do. So what we do is take the coefficients of this wavelet transform, and we save the top, and I put that in quotes because it's an important choice to make. We save only some of the coefficients. So in the song music identification apps, they take the coefficients with the largest amplitude. That doesn't work for us. It works badly. And the reason it works badly is because most of the signal that we recorded is noise. This is uninteresting for earthquake detection. So if you have sources of persistent noise and you're doing similarity search, you have to discard most of that data. In fact, discarding data is sort of what makes this routine fast. Okay, so we take just the top coefficients, and then all we say from them is not their amplitude, but their sign. So we convert the top coefficients to a binary sequence of zeros and ones, and that's our compression. So we're going to want to compare the similarity of different fingerprints in a way that allows us to find similar. Remember, we're starting with waveforms. We're trying to find similar waveforms, and so we don't use the cross correlation coefficient. Instead, we use something called Jaccard Similarity, which is just the intersection of the non-zero, the common elements of the two sets of non-zero coefficients divided by the union. And this is something that can be calculated very quickly, or approximated very quickly using hashing techniques. So our fingerprints have to have, they're important qualities they have to have in order for this to work well. They have to preserve similarity. So if you have similar waveforms on the left, different earthquakes, they should have similar fingerprints on the right. Likewise, if the two waveforms are different, then their fingerprints should be different. So we have to preserve that similarity or dissimilarity. And here's where choosing the right coefficients becomes critical. If we choose, so what's shown here, this is a trade-off curve, it's called the ROC curve. It shows the true positive detection rate on the vertical axis, and on the horizontal axis, the false positive rate. So if your algorithm is working well, making all the detections that should, avoiding the ones that shouldn't, you would be spending time up here in this corner. What's shown is for four different signal-to-noise levels of known data, the performance of the detector, if you take the largest coefficient, so you can see you're far from optimal if you do that. If you normalize by the standard deviation, then you do much better. And so you might ask, well, the standard deviation of what? What we do is we run on a subset of the data, get distributions on each of the behavior of each of the coefficients in the wavelet transform, and And then in this step, we're looking for the ones that are anomalous, that are sort of on the tails of that distribution. So if we use, under the Gaussian assumption, it gets us much closer to the ideal. And then here we use the median absolute deviation, which is more robust with respect to outliers. And that really, really cuts down on the number of false positives, which is really important because we want to run this for long times, and we don't want it like a decade or more, and we really don't want to have to sift through thousands and thousands of false detections.
Can I ask a question about
Of course.
the slide previous to this one?
Choose slides.
That one. Yeah. No,
This one.
that one. The signals are aligned there. I thought that the t-squared problem you mentioned earlier was because you compared all possible translations, because the signals may arrive at different times in different places. But here you seem to have aligned those.
That's just for display purposes to show that they're similar, but they need not be aligned. If they're shifted by a couple of seconds, we sample once every second.
Yeah.
So if they're shifted by a couple of seconds, then we'll detect them.
Your similarity measure is
Yeah.
insensitive to that. Thank you.
Okay, so this is the workflow I've just described. And so the idea is we go sequentially through all the data, one pass through all the data, and we fill the database with the pointers to the individual fingerprints that we've kept track of, and use something called locality-sensitive hashing to group similar fingerprints from some high dimensional space to a lower dimensional space, basically an integer, and they get grouped together with high probability. And then we're sort of trading computation time for memory. We have to store all this stuff, and for not, and also for comparing the similarity more probabilistic. So that's sort of the databasing technique, if you want to call it that. And so the question might be, why does fast work fast for large T? This is kind of an odd diagram, but this is just a histogram showing the number of window pairs, actually, versus their similarity. And this is a log scale. So for this is like a 2-week data set. You can see that just a couple hundred billion are not very similar, right? Window pairs that are not very similar. So those are ones that we're not interested in because we're detecting based on similarity. Then these are sort of marginally similar. These are very similar. And so the way, how this works is we go through the data once rather than, it goes like order n rather than n squared. And then we do sort of our fancy processing, post-processing on the signals that are similar and just ignore all the other ones. So we can do a runtime scaling diagram. Here's the quadratic scaling. This is runtime versus continuous data analyzed. And this is the linear or near linear scaling we get with this
Greg?
approach. Yeah.
Did you mention what the criteria are for a match?
So the criteria for match are, so it's based on this measure above a certain threshold. And so there's some latitude here. It depends on how tolerant of false detections you are. You absolutely don't want to get false detections, and you would set the threshold high. If you want to make sure you don't miss anything, you would set it low. And once you sort of reduce the size of this problem to a manageable size, hundreds of thousands or millions of potential events, then you can do the sort of post-processing that we're used to doing on manageably sized data sets to figure out which are real detections and which are those.
Is there any kind of tuning for a particular locale that has to go on?
Absolutely. It's going to depend on the noise characteristics and all that kind of stuff. But there are ways to approach that. And there are, in the way you set up the hash tables and the number of hash functions that you saw, there are degrees of freedom that require some thought. Good question. Any others? Okay, so a way to think about about this is that we sort of go through the waveforms once. We put them in a filing cabinet. That's our database. And then we forget, just like I do with filing cabinets, we forget almost everything that's in there. And every once in a while, there's something of interest, and you go and query that, and you find. So I'm going to show an application of this, the Guy-Greenbrier earthquake sequence in Arkansas. So this is a suspected induced earthquake sequence that happened in 2010, 2011. It culminated with a magnitude 4.7 earthquake that caused the shutdown of deep disposal wells. This is a zoom in on that area. So what's shown in, well, you can see it, but this is the eventual distribution of seismicity. Each one of these solid upward pointing triangles, those are seismic stations. We have only 3 instruments in this area to work with. These are deep injection wells, these downward pointing triangles. Well 1 and well 5, due to their proximity to this earthquake sequence, were sort of implicated in triggering. And so what's shown with the colored circles, these are earthquakes early in the sequence, in the first 3 months of the sequence. There are about 7 years, I think, that are in the standard comprehensive catalog of the U.S. Geological Survey. So we applied this fast algorithm to the first 3 months of the sequence because we wanted to see the initiation stages, sort of how it got going. And we found, with FAST, we found, what, 13,000 earthquakes instead of 70. And then we used those templates, those waveforms we found, to find additional events with template matching up to 1,000 or so. So suddenly we have 500 times more earthquakes to work with than we had previously. And this just shows from June to September 2010, the sort of the richness of earthquakes we have to work with. This is where injection well, in fact, deep injection well 1 started injecting, and this is injection well 5. Those are the 2 near the fault. You can see there's a lot of earthquake activity even before that injection began. As I said, earthquakes follow a power law. What's shown here are the events we were able to detect. Because these are smaller, so this is magnitude, this is the number on a log scale. Because these are small events, we were only able to locate 1,740 of them. So most of them we can't locate, but we can localize them because they're similar to nearby earthquakes. So we can assign them to locales even if we can't locate them. We were fortunate to find among these repeating events 3 quarry blasts. So quarry blasts happen at quarries, obviously, and so there's a known location. So we looked on Google Maps and then Google Earth. This is the quarry, the Greenbrier quarry, and by comparing different times, Clara was able to find the active face of the quarry. So we know exactly where these events are coming from. These are blasts at the quarry. And so that allows us to calibrate the locations quite well. So here are the earthquakes that are small, magnitude minus 1.1 to 1.8. What's shown here are the earthquakes we're locating in color. Here's the Guy-Greenbrier trend that would eventually form. Here are the injection wells. What's also shown here are stimulation wells. So these are places where hydraulic stimulation or fracking is being carried out. The way that works is there's a vertical well, horizontal laterals off of that, and this is the horizontal lateral. So we grouped these earthquakes into clusters and then looked at their spatial and temporal characteristics. Basically what we found is that the majority of these earthquakes are not related to the eventual Guy-Greenbrier sequence, but they're due to fracking. And they're small. Remember, they're magnitude 1.8 or smaller for the ones that I showed previously. So we're going to zoom in on this cluster 1 here, which was particularly, that's the one that's particularly rich. What's shown in purple are times of water injection, and then the black lines indicated there's an earthquake. So they're very strongly correlated. For this cluster 1, we were able to locate almost 700 earthquakes and associate or assign 2.5 thousands of them, and then this sort of shows the wavelet similarities. So here are the wells, here are the laterals off those wells, and you can see that these earthquakes form lines that are, or planes that are perpendicular to those wells. And so what we think is going on is that the tracking is done in stages where it starts at the end and moves backwards towards the well. And we think we're seeing actually individual stages in these operations using, remember, we only have 3 stations to work with. So fortunately in Arkansas, they release not just when the wells are stimulated, but the individual stages. So I'm going to show an animation here that shows stimulation stages happening with the color-coded by time, with the rectangles, and then it'll show small earthquakes happening in response to that. So stimulation begins on this well. You can see the earthquakes. Track it pretty closely. Then they start simulating the other well, and that starts lighting up. Well, so all these small earthquakes that we're tracking here were not in the catalog. That we were able to find them and to locate them with just 3 stations, and it shows very clearly that the timing, the spatial association, even the sort of morphology of the sequence follows the simulation.
Greg, just a short question regarding the difference between the template matching catalog and the catalog you produce with FAST. Did you look at, presumably you looked at the template matching events that FAST did not identify. Were there characteristics of them for some reason FAST wouldn't identify, or are they mischaracterized by template matching?
So the characteristics were they were small. And so with template matching, you typically have one fairly high signal noise ratio event that you're matching against low SNR events. With FAST, you're trying to match potentially low SNR with low SNR, so that so FAST is not as sensitive to template matching. So we expect there to be additional power for running the templates that FAST discovers through continuous data. That's what we did. Okay, so we wanted to understand this these sequence. Basically, we can't determine the focal mechanisms. All we can say is it's inconsistent with the expected direction of shear. In fact, it's, if anything, opposite to the extent that we have data, but the data is very sparse. So the conclusions from this part of the talk are that most wastewater injection but primarily hydraulic stimulation are triggering earthquakes here. What we really need to do is go forward in time when the sequence, the main sequence gets started. Claire's going to graduate, so she's not going to do that. But in order to figure out what was going on here, we really needed precision seismology and this detailed injection data. But that gave us a clear picture of what was going on. So I'm going to talk just a little bit about some progress on FAST for long duration problems. So computer scientists got involved. They made it run 100 times faster. Embarrassing, but useful.
So
and
what
they sort of reduced the memory bottlenecks that we were.
So what was the speed up due to? Was it due to the locality sensitive hashing types of optimizations, or what were the dominant?
So there were a number of things, but it was primarily, a lot of it had to do with the way we were setting up our hash functions. That we were using a random number generator.
As opposed to like the Jaccard, like min hash type.
No, it was still using Jaccard. We were using, I forgot now, something like truncation. There was some thing where we changed, I think it was the way that things were randomized, and suddenly it went much faster. But there were multiple things, including memory management, multi-threading and stuff that I don't remember. But it's great now. So we're planning to release this publicly. I haven't done that before, so ideally the first half of this year. And just pointing out that we can now run it on 10 years of continuous data. Now, when you run it on these really long duration data sets, you get even if your false positive rate is low, you're going to get a lot of false positives. So the way to suppress that is to do the detection over a network. So here's sort of our flow chart of our algorithm as applied to a single channel. The output is a very sparse similarity matrix. So it's just, we threshold the similarity, we just say triplets, so the time 1, time 2, and similarity measure. And we can do that over many channels. For an individual channel, the similarity will persist for a certain amount of time, but the relative time of event 1 and event 2 is preserved. So if we plot time 2 versus time 1, this property of constant relative time means that the similarity will be spread out in sort of a cloud along the diagonal. For detecting over a network, we're doing this pairwise with a pair of times, and the relative time is preserved. Even though the phases arrive at different times, and they arrive at different times at different stations, we get for a single event, we get our similarity spread out along a diagonal of this similarity matrix. So we come up with an algorithm to sort of capture those shapes and analyze them, and this dramatically reduces the false detection rate, allows us to the threshold lower. And if you can imagine, sometimes it's simple like this, where there's a nice clear diagonal for two strong waveforms. Sometimes the events are a little bit dissimilar, or they're similar on the P wave and the S wave but not the coda, so we get interruptions. Here again, like Paul, there are things that you have to adjust depending on your situation. And of course, sometimes it just gets messy. It's inevitable since we're trying to detect small events that we're going to be operating near, operating low noise ratios. Anyway, the Iquique earthquake happened off the coast of northern Chile, and it has been extensively studied using template matching, and we were able to detect 580 new unrecognized events in the 17 days before it shot. So I'm running out of time. It's possible to make this more efficient using all-to-sum search. So the idea here is you database a subset of the total data, and then you query against that with all of the data. And for the Iquique case, we were able to dramatically reduce the runtime and still get nearly all of the events. This is the way you would do it for real-time processing. So in conclusion, seismology has these very large data sets, and they're getting larger quickly. We developed an algorithm that enables sort of data-driven discovery. It's best suited for sparse networks and signal-noise ratios that are not too low. So we need different approaches, I think, for dense networks, where we have common signals on nearby stations, and also for low signal-to-noise ratio cases. We've been working on machine learning techniques for detecting P and S waves. We have a big advantage over many fields in that we have massive labeled data sets that are ready to go. So we have tens of millions of P wave and S wave waveforms that can be used to train nets. And this will allow us to generalize sort of strict similarity measures. And so far, this preliminary indicates it works very well at picking individual cells.